Hello class, today is Wednesday, June 17th, Coronachem, day 49. We have today and tomorrow to learn some more organic chemistry. Tonight, I would like you to find and name all the isomers of C5H10. I'll write down the question at the end of the class so you could look it up. The answer is on one of my playlists. In nomenclature you'll find it. There's two such questions. That's what I'm going to ask you for the test, something like that, maybe a couple other very easy questions. So briefly then, alkynes. They are hydrocarbons that contain at least one triple bond. Their suffix is "-ine", Y-N-E. And an example of that is pentyne. You see there's 5 carbons here, 1, 2, 3, 4, which I drew badly. Let me redraw that so you don't get confused from it. There's the 4th carbon, and then at the 4th carbon you have the triple bond. Because of sp hybridization, the bond angle is 180 degrees. So when you draw that part of the molecule, everything that comes off the triple bond is sticking out straight. So for example, if you were to draw acetylene, which is C carbon C, C triple bond carbon C, the methyl groups that were to come off it, or the hydrogens that would come off it, come off at a 180 degree angle to the main bond, okay, because of that sp hybridization. So whenever you draw the alkynes, just remember that part is straight. So much so that if you have a cyclic alkene, that's okay, but a cyclic alkyne is highly strained, so that this compound is highly unlikely. I mean, I think it's possible, but it's highly strained, so it would probably be very, predictably, would probably be very reactive. To have no strain, you would have to have a very much larger cyclic molecule so that those bonds could stay straight, and then the rest of the molecule would go around in a circle. But that would be, my prediction is that would be a very strained molecule because of the fact that the triple bond wants to stick out straight on either end. Here's another example of a molecule with a triple bond in it. So it's an alkyne. 1, 2, 3, 4, 5 is the longest chain, but the second carbon is part of an alkyne, C triple bond C, and there's also a methyl group at the 4th position. So you would say 4-methyl, 2-pentyne. It's named as a pentyne because alkynes have a higher priority in the naming chart than do alkanes. So the numbering is from the side that will give the lowest number to the alkyne. Alkenes and alkynes are chemically reactive at their double and triple bonds, which will now begin my next section where I show you some of the reactions that alkenes, and alkynes can undergo. Typically, alkanes are quite unreactive because they don't have high electron densities in the areas where you might want the reaction to take place. But let's take something like ethylene, and if we add bromine to it, what you'll get is something like this: dibromoethane, 1,2-dibromoethane. And this reaction is called the bromination of an alkene. So alkenes can be brominated. Any halogen tends to add across double bonds. In fact, it's a test for unsaturation. One of the first organic chemical reactions I remember seeing in college was the bromination of bacon. So what the chemists did is they put a strip of bacon inside a bell jar. They evacuated all the air, and there was a jar of liquid bromine sitting next to the bacon. And when they evacuated the air from the jar, the bromine started vaporizing out of the beaker, and it sort of wafted over to the bacon, and the bacon started bubbling as though it was cooking. So what was happening is the bromine was reacting with the double bonds in the unsaturated fatty acids of the animal fat that was in the bacon, and it was reacting to brominate the bacon. So we saw bromo bacon. Not sure I'd want to eat that though. Although, mind you, you do find brominated vegetable oil in some drinks. They add bromine to certain vegetable oils that they add to pop, because the oil would not otherwise stay mixed with the water. So by brominating it, it increases its density so that it has roughly the same density as water, and it stays in suspension. I try to stay away from things that contain bromine. Bromine is probably not good for your metabolism, because it probably interferes with any biochemical processes that contain halogens, like, for example, your thyroid. Your thyroid makes a hormone called thyronine that helps regulate your metabolism, and if you absorb too much bromine, I suspect it might interfere with that process. So don't drink things that have that ingredient. I always avoid it personally. Here's another reaction. If you take an alkene and you expose it to hydrogen gas over a nickel catalyst, probably powdered nickel, at 500 degrees Celsius, it hydrogenates it. It adds hydrogen across the double bond, so that you go from butene to butane. So you hydrogenate the alkene, and it's called hydrogenation, surprisingly enough. You've heard of hydrogenated vegetable oil? Boom. Maybe they don't use this process, but they could, I suppose, as long as you're not getting nickel in your food. If you take an alkene and you add hydrobromic acid, you're going to get hydrobromination. So there'll be a bromine on the end of the molecule after. This is called hydrohalogenation of alkenes. Another possible reaction is if you take an alkene and you add strong acid like sulfuric acid, you can get, if you add water to an alkene, but it has to be catalyzed by a strong acid like sulfuric acid, you will get acid catalyzed addition of water. Now, if you have a butane, which has triple bond, it gives you a more reactive center, so that you can hit the same chemical twice in the same spot because of the extra electrons available to react. So if you have butane, 2 butane, 1, 2, here's your double bond, 1, 2, 3, 4, that's 2 butane. And if you expose it to chlorine gas, you will end up with a substituted butene. It will become trans 2,3-dichloro 2-butene. So it's called partial halogenation of an alkyne. If you were to expose the same molecule to more chlorine, to a higher concentration or pressure, I don't know the exact conditions, but again, 2-butane as a starting product, you would get more chlorination of the molecule. So now what you would get is 2,2,3,3 tetrachloro butane. And that's called exhaustive halogenation. Of an alkyne. sometimes when they show reactions taking place, they like to do what are called mechanistic arrows. They show what the electrons are doing when they react with one reagent or another. So that they try to explain what are the likely routes of interactions when the molecules are colliding. So it's called giving a mechanism. So let's show you what it looks like. So if you have butene, 2-butene, and you expose it to hydrobromic acid, they'll show the pi electrons of the butene attacking the hydrobromic acid, and that's going to cause this bond in the middle to move over to the bromine. This is going to open up an area here where there's going to be a positive charge. You're going to get what's called a carbocation. So you get a carbon with a positive charge temporarily. They're usually intermediates. They're not extremely stable. They don't last very long. So your carbocation is going to be over here. And then the bromide ion is going to come along, since now it's got all the electrons that it wants for its octet, but it's got a negative charge, so it's got a little higher charge density. It's going to be attracted to that positive charge. And the last step of the reaction is fast, and what you get is bromobutane. So this is called addition of HBr to butene. So I'm going to write that over here. If you have space on your paper, write it there like I wanted to, but I ran out of space because of my minuscule blackboard or whiteboard. Addition of HBr to butene. You can get molecules that have a pretty high on saturation and are cyclic. They're known as aromatic compounds. So benzene is an example of that. Benzene was discovered for the first time in the tubes that we're using to supplement, to fuel gas lights in London, I think. The people who were maintaining the gas lights, they would light them at night when it got dark. And because they were piping a lot of gas through the pipes to continuously supplement the burning of the lamps, there were trace amounts of benzene in the gas that was in the natural gas that was used, and eventually it made an oily deposit on the inside of the tubes. When they analyzed the deposit, they realized it contained 6 carbon atoms, 6 hydrogen atoms, and for a long time people were not sure what the chemical structure of this molecule was. Remember, there was no NMR or IR spectroscopy. The chemistry was in its very early stages. But a guy by the name of Kekulé had a dream one night. He was pondering the problem, and he had a dream of a snake eating its tail. So suddenly it gave him an inspiration. He woke up and he drew the molecule as a cyclic molecule with 3 double bonds, and it turned out he was right. So benzene is an aromatic hydrocarbon. So you'll see things like benzene. So that circle means there are 3 double bonds in there, and they continuously delocalize so that you get basically you can draw 2 structures that are equivalent, and it's basically the best way to symbolize that is to just make a circle. Another commonly known aromatic compound is naphthalene. It's the stuff they use in mothballs. It's toxic to insects. And anthracene is a black substance that forms when you burn coal. It forms in pretty high concentrations in chimney sweeps. And any time where you have high temperature but insufficient oxygen, you'll get the formation of anthracene, which happens to be somewhat of a carcinogen, if I'm not mistaken. They discovered this in the times when chimney sweeps used to be in fashion. People would go to your roof and they would lower a big brush on the end of a chain up and down your chimney stack to loosen all the creosote and the buildup that was inside your chimney. And they found the men who did that for a living had something like 12 times higher rate of testicular cancer. So there was something in the soot that was toxic to metabolism. Turns out it was these molecules because they are what are called intercalating agents. This molecule is so flat, it's almost like a leaf, and it can insert right into your DNA. It slips right into your DNA, and when your polymerase comes along to translate the DNA during cell division, the polymerase sort of trips on that intercalated molecule, and it could create a mutation. Usually your body can fix it, but if 1 of a million escapes, you can get a mutation that persists, and then it can give rise to all kinds of problems in your cells. Usually your body will kill off cells that are mutated, but sometimes they escape detection, and that's how you get cancer. That's why smoking is so bad, because when you're smoking, you're breathing in literally thousands of different chemicals, all of which your body manages to metabolize over time, but each time you're doing a little damage to the cells repair them, and then 1 in a million though escapes detection, and that's where your problems start. When you're young, usually it's not a big deal, but as you get older, your immune system is not as vigilant. The delocalization of pi electrons in aromatic compounds leads to their relative, I'm not going to say, it's not going to say they're unavailable, their relative unavailability. For reaction. Or aromatic compounds usually require vigorous reaction conditions. For instance, if you want to make TNT, you got to boil the mixture that produces it for hours with harsh chemicals, strong acid, a mixture of 2 strong acids, to get those nitro groups to add on to the benzene ring to form what we call TNT, trinitrotoluene. It's a high explosive, one of the early ones that was used. So, for example, if you take benzene and you add nitric acid to it, you're gonna also need some sulfuric acid to help make the nitric acid into a nucleophile, because sulfuric acid is so strong it makes nitric acid stay protonated, and it ends up giving it a positive charge, so that the benzene can actually, the pi electrons from the benzene can actually attack it. Anyway, if you want to nitrate benzene, it's not horribly difficult as long as you have the 2 strong acid, but progressive nitrations after that require increasingly more vigorous conditions. This is called the nitration of benzene. So you get nitrobenzene. If you subject it to the same reaction conditions again, you will get dinitrobenzene. Plus some more. You get mainly meta isomers. Now, when you stick substituents on benzene, you can put them the closest that they'll go together. That's called ortho. If you put them 1 space removed, it's called meta. And if you put them 2 spaces removed, it's called para. So ortho, meta, para. You mainly get the meta isomer. When you dinitrate benzene. And so the possible, I'll write down what I just said. possible isomers of benzene. So let's draw our three possibilities if they're dinitrated. You could have the ortho isomer, so this would be called ortho dinitrobenzene. This would be called meta dinitrobenzene. May come from the Italian because, or the Latin, because in Italian meta means half, so it's halfway there, I guess. And then NO2 would be para, so para dinitrobenzene. They have melting points that are slightly different. This one's at 118 degrees Celsius, this one's at 90 degrees Celsius, and this one is 174 degrees Celsius. Give it some thought in the textbook. They ask an interesting question. They say there are only two isomers of nitronaphthalene. All the other possibilities are the same as the two already mentioned if they are flipped over, right? So if you draw nitronaphthalene, you'll see what I'm talking about. Here's naphthalene. You could have it like this, or you could have it like this. Those are the only two isomers that exist, because everything else you could draw is the same thing, just flipped over. Okay? So I could draw this, put the nitro over here, but if I flip it over, it's still the same molecule. I could put this nitro over here, but I flip it over this way, it's still the same molecule. So those are the only two isomers of nitronaphthalene. Here are a couple reactions for benzene with bromine. If you add some bromine to benzene, you got to use a catalyst to make it work, otherwise it doesn't react. It's iron tribromide to help catalyze the reaction. So it's a catalyst. And what you get is bromobenzene. Bromobenzene, not particularly useful as far as I know, other than as a chemical for producing other chemicals, because it's pretty toxic. Most benzene substances, you just don't want to mess around too much with them, just play it safe. Don't get them on your hands. Not that you should get any other chemicals on your hands if you want to be safe. But I remember reading stories about they used to have polychlorinated biphenyls, which are benzene compounds, as an oil in transformers, because polychlorinated biphenyls don't burn easily. They resist the flow of electricity, and they resist being broken down by heat, so they made an ideal liquid for insulating transformers. Old electrical experts used to clean their hands with this stuff. It was a great solvent, but then it was discovered that it causes cancer. So, it's always better to play it safe and not expose your skin, especially to substances that can go into your skin and then get into your body, because then they end up on your liver and they can cause liver damage. Your liver filters out all the chemicals that are in your body, and if your body doesn't know what to do with it, your liver tries to oxidize it so that it can become more water soluble, so it can be filtered out by your kidneys, and then you can urinate it out. But the whole process of your body trying to detoxify chemicals sometimes backfires, and your body makes it more toxic. So then you have a problem, because your body's trying to get rid of the substance, but it actually ends up making it either to a carcinogen or something that damages cells. So this is called the bromination of benzene. this is called the Friedel-Crafts alkylation. Let's see how much time we have left, because I'd like to give you a chart. Yeah, we have 5 minutes. I'll give you at least part of it. And I'll give you all the functional groups that you should become familiar with. Like it or not, you will become familiar with them in university. So here's the functional group. Type of compound, suffix or prefix, depending on how you have to name it, and an example and name using IUPAC, systematic naming. So first functional group is an alkene. So alkenes have C double bond C in them. You can have R groups attached off of that, of all kinds. That's an alkene. The suffix is -ene. An example of an alkene is butene, like over here. But let's draw it in bond line. This would be called 2-butene. Then we have alkynes. Here's the simplest alkyne you could draw. It's got an "-ine" suffix. The simplest alkyne in bond line notation looks like that, if these are hydrogens, mind you. So that would be called ethyne, because it's got 2 carbons. It's also called acetylene. It's the most commonly used welding gas, because it burns at a very high temperature with almost an explosive flame. It's actually dangerous if you get a lot of acetylene in one spot and it's mixed with oxygen. You can blow stuff up, or you have to be very careful. You can blow yourself up. They always say, when you turn off a torch, do it in alphabetical order, C before O, or up you go. So you turn the carbon off first, and you turn it on in the same order. Turn on the carbon first. So when you turn on an acetylene torch, you spark it, and it makes a big smoky orange flame. Then as soon as you start adding, actually it might make a white flame if there's enough oxygen, but it's not explosively. It doesn't burn explosively because the gas is coming out of this very fine pinhole. And then you turn on the oxygen. As soon as you turn on the oxygen, it comes out like a jet, and it gets loud. And then you can cut steel with it because it burns at 3,000 degrees Celsius. It's a very useful material. The next thing is an alcohol. Alcohols, they're all kinds. They end in "-al" when you name them. So for example, if you had 2 carbon atoms and then there's an OH group attached to it, that's eth for ethane with an OH on the end of it, so it's ethanol. If you have 2 R groups attached to an oxygen, then it's called an ether. You just put ether at the end of the name, and you say alkyl, alkyl, ether. So, for example, if you have 2 ethyl groups, here's your oxygen atom, you have an alpha group on one side and an ethyl group on the other side, so ethyl, ethyl, ether. Or you could say di-ethyl ether. Yeah, let's go to the end of that chart. You'll have to use the magic of pause if you want to see all this and copy it down. If you have an R group with X symbolizing any halogen, so fluorine, chlorine, bromine, iodine, good luck with astatine. You won't find any on the Earth. That's not radioactive, so we're not going to mention it. So haloalkanes. Usually it's a prefix. You're going to say halo, halo. And here's an example. You could have a methyl group with a chlorine on it. That would be called chloromethane. If you have 2 chlorines on the methane, you call it dichloromethane. If you have 3 chlorines, trichloromethane, it's also called chloroform. And if you have 4, you call it tetrachloromethane, but it's usually called carbon tetrachloride. A lot of chemicals have what are called trivial names. So there's the official IUPAC name where you follow the rules to the letter and you get a name. And then there's the trivial name, because very often chemists name something that's in common use, but because if you name it the official way, it ends up being a mouthful, you know. So for example, ketones can be named alkyl ketone. So there's an industrial chemical called methyl ethyl ketone, or you could call it methyl ethyl would be there's 4 carbons. 2-butanone would be the official name for it. And you could also, they call it MEK, M-E-K, methyl ethyl ketone, because, oh, get me the MEK, get me the barrel of MEK, because, you know, construction workers or chemistry workers don't want to sit there and name big long things. They want to get to the, cut to the chase. So a lot of these will have trivial names, also because they have a long history of being used. So they were named before the system was made so systematic. So even within the IUPAC naming system, there's a rule that says judicious use of trivial names is encouraged because it helps to shorten the name. And if everybody calls something phenol, you're not going to go around saying, "Oh, give me a container of that hydroxybenzene." People will look at you funny if you say hydroxybenzene is phenol, that kind of thing. All right, so another category of chemicals has nitrogen with R groups on them. Those are called amines. Some people say amines. I don't know. I've always said amine. Amines are usually pretty stinky, especially if they have a lot of alkyl groups on them. They smell like fish. They have a fishy smell. So they're not pleasant substances to, here's a simple one. 2 carbons with a nitrogen group and then hydrogens coming off of it. This would be called, because it's 2 carbons, ethylamine, so ethylene. Aldehydes, now you have chemicals with carbonyl groups in them. A carbonyl group is a C double bond O. If you have a C double bond O with an H attached to it, that's called an aldehyde. So there's an R on the other side, which would be any sort of chain with carbons on it. That's called an aldehyde. And it's got an al suffix. So if you put al on the end of it, you're saying it's an aldehyde. Here's an example of the the simplest aldehyde has an H and an H on both sides. And that's called formaldehyde, or methanal. It's also called formaldehyde, because it reminds people of formic acid. Formaldehyde. It's kind of a toxic substance because it reacts on both sides, so it's a good cross-linking agent. If you breathe formaldehyde in, it cross-links your proteins. It can give rise to allergic reactions, and there was a problem with a form of insulation they used a few years back where they were using urea and formaldehyde to form an expanding foam insulation. But what happened is when some of the formaldehyde would remain unreacted, and it would be sort of stuck in between the rafters of your house, and then over the years it would leak out into the air of the house, and it caused toxic problems. People were having asthma from it, so people ended up having to rip it all out of their house because they were having chemical reactions in their lungs from it, and that was not a good thing. So it's always important to test the long-term effects of any chemical that you wish to use for industrial applications, especially if the public is going to risk being exposed to its residues. If you have a carbonyl group with 2 R groups attached to it, then it's called a ketone. And ketones have an "one" ending on them. An example of the most popular ketone, I don't know if they still use it, they used to use it a lot, acetone. They call it acetone. That's a trivial name. It's actually called 2-propanone if you use the official naming. 2, because there's 3 carbons in a row, 1, 2, 3. The second one is where the carbonyl is, so you call it 2-propanone. It's also called acetone. That's its trivial name. If you have an R group attached to a carbonyl and then an OH, that's called a carboxylic acid. And the way you name it is you put oic on the end of it and then you say acid. And here's an example. One of the ones that are most popular, you'll probably put this in your salad. It's called ethanoic acid because it's got 2 carbons, 1, 2, and then that OH on it. This proton comes off, that's why it's an acid. So ethanoic acid, it's also known as acetic acid. That's I suppose it's a trivial name. And then you can have what are called esters. Esters are usually pleasant smelling, fruity substances. They're used, there's a whole class of them that are used as flavoring agents in the food industry. You can actually buy books that tell you what the chemical that gives a certain flavor is. So when they say on the ingredients natural and artificial flavors, that's what you're looking at. It's probably some kind of ester they're adding there to give you that taste. So esters have an O8 ending. And then they name the thing that's attached onto the oxygen first. So for example, if you had let's say you had an acetate group and then a propane group, 1, 2, 3. So that we would call this propyl ethanoate. All right, so the ethane because there's 2 carbons on this part, an O8 ending on it, and then propyl because there's 1, 2, 3 carbons attached to that oxygen. So you would call this propyl ethanoate. And are very popularly used as flavoring agents. Last one is amides. Amides are, oops, I should have drawn the chemical first. Let's draw something with a carbonyl group and an R group on one side, then it's got a nitrogen group, and it's got 2 other R groups attached to it. Those are called amides. Now, they don't have to be R groups, you could have 2 hydrogens, it would still be an amide. Amides are found more widely than you might realize. Your proteins in your body have an amide group in them. You would say amide as a suffix. An example of an amide. One of the simpler ones, acetamide or ethanamide. Ethanamide. It's also called acetamide. And whenever you put a substituent on the end, you'll say N something. So if you were to say, let's say you put a propyl group, 2 propyl groups, you would call this 1, 2, 3, 1, 2, 3. Yeah, you would say N dipropyl ethanamide. So the NN tells you where these groups are on the nitrogen and what they are. You could have also N, say propyl, and ethyl, if it was this instead, then say ethanamide. Okay? Okay, that's enough on nomenclature. What I'd like you to try for tonight's homework is look up, well, the answer is there if you can't get it, but what I'd like you to do is give me is the list and name question. List and name all of the isomers of C5H10. Remember, this is not a saturated alkane. It's missing 2 hydrogens, which means it's either got 1 double bond or 1 ring. So here's your hint. Has 1 double bond or 1 ring. And I'll explain why tomorrow. The answer is in playlist called Nomenclature, and you'll find it in there if you look around. It's in there. Okay, so we'll see you tomorrow. And tomorrow is our last teaching day, and then Friday I'm going to give you a test, and then you'll have all day Friday. I want you to hand it in by Friday evening, and I'll have the weekend to mark it, and then that's it, folks. That's the end of the year. Congratulations if you're graduating, and come and say hi sometime.